Hi and welcome to this tutorial on reactions with halogens. In the previous tutorial, I introduced halogens. We talked about some of their trends as we move down group 7. And here we're going to be looking at the oxidizing ability of halogens. We're going to look at the reactions of them with group 1 and group 2 elements and their reactions with hydrogen 2. Let's talk about oxidizing ability first. So as we move down the group, we would say that their oxidizing ability decreases. Now, when we're talking about their oxidizing ability, we're talking about their ability to take an electron, because they need one more electron in their outer shell to satisfy and have the noble gas configurations. They're trying to get that extra electron. They've got 7, they need 8. So it's how good are they at taking that electron off another element? And that other element would be oxidized. Oil rig, oxidation is lost. They would be oxidized. So we talk about it in terms of the halogens oxidizing ability as an oxidizing agent. So it's going to decrease. Fluorine's very, very good at nabbing electrons off other compounds, whereas as we move down, they get worse and worse and worse. And why is that? Well, as we move down the group, we are increasing the atomic radius, and it's always a lot more dramatic when you see it visually like this. You can see the huge difference. And so the distance between the nucleus and the outermost electron is going to increase and increase and increase. So it's got a much, much greater shielding effect. There's lots of stuff in the way between that positive nucleus that is trying to attract an extra electron. So this nucleus here is desperately trying to get another electron in its shell all the way over here. But there's such a big difference, okay? So if we're going in this direction, we're saying there's an increased distance between the nucleus, the positive nucleus, and the outer electrons. And that's due, and that's linked to the fact that we've got an increased atomic radius as well. So there's a decreased atomic radius and there's more shielding. There's both of these factors at play. So like I said, the halogens, they're wanting to gain that final electron into the outer shell to get it its noble gas happy configuration of 8. So it's all about how easy or difficult is that for that halogen to be able to do that. So as we move down the group, the reactivity is going to decrease for the reasons we've just discussed. The halogens are become less reactive because the atomic radius increases as we move down. And this means the distance between the outermost electrons and the positive nucleus increases as we move down the group. So that's reducing the attraction of that positive nucleus between the positive nucleus and the outermost shell. So it's more difficult to gain that extra outer electron, okay? So the halogens are going to also become, that means they become less reactive. And it also means that their oxidizing ability is going to decrease because their oxidizing ability is another way of saying their ability to get that extra electron. So halogens become less oxidizing as you move down. Fluorine is a really, really strong oxidizing agent. Displacement reactions involving the halogens are a good test for their oxidizing ability. So in a halide, in a solution, will only displace a halogen that is above it in the periodic table. And we can have another recap of it now. Okay, so chlorine is just going to be able to displace bromine and iodine because it lies above them in the periodic table. Bromine is going to be able to displace iodine because it sits above it. Iodine does not react with, fluorine, chlorine, or bromine because it's the least reactive at the bottom. And you can see this as a description, the ionic equations going on here. We can also use displacement reactions to just identify the compounds that are present in the solution, or the ions, the halogens present in the solution. So what we're going to look for is the color change. It's a qualitative test. We're looking for a particular color change. So we know what the color is for a positive test result, and we can compare it to the table below. So if we react chlorine that's been dissolved in water with sodium chloride, we are going to get no reaction in this particular case. Of course we're not, because the halide's the same. And there's going to be no reaction here because we're talking about bromine, and there's going to be no reaction here because both are iodine. But if we react chlorine with bromine, with a sodium bromide, then the chlorine is going to be able to displace the bromine in this particular case. So we are going to end up with Br2 being formed. And so we're going to get an orange solution. So we're going to get Br2 and we're going to be ending up with NaCl, and that's not going to have any colour. But this in water it's going to be an orange solution. And that's why in the previous tutorial it was essential that you learnt the colours. And chlorine is also able to displace iodine. So we are going to end up with iodine being left. And what's iodine's colour in water? It's going to be brown. So we're going to see a brown solution. And of course, we're also going to end up with NaCl because that displacement, and that's not going to have any colour to it. We're not going to get any reaction with bromine and sodium chloride because bromine is below chlorine in the periodic table. So no reaction. But my bromine is going to be able to displace iodine. So we're going to end up with iodine, and so a brown solution, and NaBr, which is colourless. It's just a salt. And then we will have no reaction going on for any of these because we know that iodine cannot react. It cannot displace any of them because it is lower down in the periodic table. Halogens can react with group 1 and group 2 metals to form halide salts, and it's a typical redox reaction. So in this particular case, the halogens are going to get reduced and the metals are going to get oxidized. And let's give an example. So if we talk about group 1, we're going to have lithium, solid lithium, reacting with fluorine, and it's going to make lithium fluoride. And I'm going to balance that, and I have to put a 2 here and a 2 here. That's actually a solid, and of course that's gases at room temperature and pressure. So if we talk about the oxidation states, our lithium is going to be 0 because it's an uncombined element, and fluorine is also going to be 0 as well. And then our lithium, it's now in a compound and it's in group 1. So it's going to be a +1 oxidation state, and fluorine is always -1. Okay, so we can say that fluorine has gone from oxidation state of 0 down. It's gone down the number line. So fluorine has been reduced. And my lithium has gone from 0 up. So it's been oxidized. It's got an increase in its oxidation number. So what about group 2? Let's give an example of magnesium. So that's going to react with chlorine this time. And so we're going to make magnesium chloride. Let me balance that just so. Magnesium chloride, and that doesn't need to be balanced because it is already nice and balanced. So in terms of our oxidation state, we're going to have 0 for magnesium to start with. Then it's going to go to +2 because it's group 2, so it's always +2. And chlorine is going to be 0 to start with, it's an uncombined, and it's going to be -1. Each chlorine atom itself is going to contribute -1. Remember, we don't do it as a total, we're going to talk about each individual atom. So we've got -1 because it's not an exception, and these oxidation numbers must add up to 0. So 2 + 2 times 1 -1 is 0. So what can we say? We can say that chlorine has been reduced. And in the exam, I'd give the numbers from 0 to -1. And then I can't fit this on the page, but we can see the magnesium has been oxidized from 0 to +2. Halogens can also form covalent bonds with hydrogen to form hydrogen halide molecules. And there's some examples here. And the vigor of these reactions decreases as you move down the group. Okay, so the vigor of which this happens decreases. So you can see here, fluorine reacts explosively in cool, dark conditions, reacts explosively in sunlight, slowly on heating, and just forms an equilibrium mixture on heating. And the thermal stability of the hydrogen halides decreases as we move down the group. And this links to the thermal stability that we've talked about before in terms of quite a few things in group 7. So as we move down the group, we're going to get an increase in the atom sizes, and we're going to increase the distance between the atomic nuclei, the positive atomic nuclei, and the shared electrons in that bond. Okay, so that distance is gonna increase. So the strength of the covalent bond as we move down the group is going to decrease. And so the temperature required to break that bond and the length increases as well. So the temperature or the energy required to break that bond decreases as we move down the group. So it gets easier and easier. So that's why we say the thermal stability of the hydrogen halides decreases as we move down the group.